All right, hello, welcome back from fall break. Those of you decided to make it only a half week and not a full week. And welcome back from the midterm as well. So the midterm solution sets are available on Canvas. You can also look at your stage one and stage two. I think stage one requires you to go through lockdown in order to see your results. But stage two, you should be able to see the results and the solutions just, without that. But there's also a PDF solution set, if you haven't seen that, that has all of the solutions on it as well. So all of that's available. If you have any questions, please let me know. If you didn't notice, I did send out an announcement with the distribution from stage two, and then I tried to sort of address all of the questions that continued to be, well, not continued to be, but didn't have as much improvement as other questions. So all the questions had improvement, but there were some that were still difficult. And so that's the nice thing about these stage one, stage two, is it helps me filter out the problem or the questions that are are more difficult to the point where you couldn't sort of where a lot of things like if I from stage one it turns out some of those you sort of end up being able to kind of fix on your own, and the other ones are things that it's good for me to know that are were apparently were more difficult. And so if I have opportunities then to do kind of just in time updates of those the rest of the semester I can, or it just sort of helps me thinking about the next time I teach. So that's useful feedback for me to see those sorts of things. But if there is still something that's lingering for you after stage two and after that announcement, please feel free to reach out to me or the TA to ask those questions. Say, I still really don't get this random numbers thing or whatever. So because that would be a good time for that, because most of the content we have moving forward is going to be moving forward. So it's going to build upon that stuff. But largely before the midterm, we were kind of modeling in probability. After the midterm, we're largely statistics. So it's sort of be a little bit of a shift in the feel as we kind of move more towards data and stats and away from probability. But still, that stuff's really important, and it's we're building upon that. So feel free to reach out if you do have those questions. The labs, there's so this lab 8. So I think I think I might have pulled this from a presentation that might have been offset a little bit here, but but what I'm trying to talk about is here. Lab 8 is a data collection and input modeling lab. So this um, so th this so is going to help you sort of figure out that so how to sort of say this. So there is a final project. So I guess I should have led with that. So as it said at the end of your midterm, the final project is something we have to now start thinking about. So the first deliverable you have for your final project. So your final project is sort of like, the final project allows me to not have to worry about giving a second midterm. So we just have one midterm and a final exam. And the final project takes up a chunk of your grade that might in other courses be used for a midterm. The final project will be graded a lot easier than a midterm. So there's that kind of, and a lot of parts of the final project are easy tick boxes. So like, what a fraction of the final project score is submitting the names for your final project teams. And so these are teams that ideally, this is a relatively small class this semester, so I might be able to permit more 3-person teams, but ideally 4-person teams for logistical reasons. So some of you, it might be easier for you to find teams, others not. So in the final project module on Canvas, which is on kind of on top of, before all the units, I have a link to just a Google Sheets doc that anyone can edit that kind of shows a format up at the top where if you're looking for additional people to add to your team, or you're just looking for a team, it's meant to be a clearinghouse to help make those connections. And as I see teams submissions coming in, I'll also sort of like, eventually gets to the end of there. And if I notice there's certain students that are unmatched, then I can try to do some matchmaking myself. But it's a lot easier for me if you try to do that as much as you can. So you'll submit your final project teams, and that is, I think, due it's not due this week. I think it's due next week. But I'd have to double check the dates, because again, I feel like when I was reviewing the slides for today, I just buzzed over this one, and I really think this is offset. So it says on Canvas and in the tentative schedule exactly when the teams are due, and I really think it's next week. But the idea here is that every one of those four members of your team submits this individual assignment with it's just a text box, and you just put the four names. And that way, when I go through and grade them, I can just make sure, okay, these four all agree that these four are in the team, and I'll put you in a Canvas group. And then every other final project assignment, except for the peer review, will be a group assignment. So only one person will need to submit that. So that's your first thing. You get a good chunk of your final project score just from submitting that. And then a couple weeks after that, you submit this input modeling report. And so in that case, you're going to then tell me what your plans are for what real world system that you're, sure or not that, yeah. So what real world system that you plan on working on. So it could be, like a grocery store, a cafeteria, a traffic intersection. It could be the walk only zones on campus. It could be a Starbucks on campus. A food service place, you could sort of study something that has an interesting operations research problem that you plan on solving. And so in this input modeling report, what you're basically going to say is, we've picked this system. Here's the general rationale for why we've picked it. We noticed long lines, and it seems like there's some opportunities here that we could try some things. And then I want you to then sort of list, because we're going to be starting about input modeling here, what do you think are the inputs to that system? So what are the things that you're going to need to gather data on? And so that might be like the inter-arrival times, the service times for particular, for how long it takes to make a coffee, these sorts of things, and so on. And then I'm going to hopefully you go out and actually gather some data. So in the input modeling report, which we do about 2 weeks after the team names are done, I don't need you to gather all of the data for your inputs, but I want you to demonstrate the ability to gather data on that system. And so you can go out there and sort of say that, you may have some expectations that, that what types of distributions, certain ones of those inputs are going to be, but then also see that, actually we've gone out and we've gathered data on the, pilot data on the inter-arrival time distribution. And here is a histogram of it. And we've used tools from this unit that we're starting now to sort of decide that this inter-arrival distribution is best fit as a Weibull distribution or something like that, and then sort of justify that to me. So then it shows me that you have access to the system, you can get data from the system, and you've picked, what inputs you need to get data from eventually to do the full final project, and you are comfortable enough to actually then fitting models that you can then put into Arena as you start diagramming it up. And so that's kind of the motivation between this input modeling report that is coming up. And so you'll do that, and then they kind of leave you alone for the rest of the semester. And then in the last week of the semester, you're going to upload a 4-page report with a very specific format. So it should be pretty easy to fill out. And then a 10-minute, no longer presentation video from your group presenting your results as if you're presenting it to a stakeholder. So it's not presenting it as to the class or something like that. And in the past, I've used Canvas peer review to do peer reviews of the reports and the presentations. This semester, I'm going to experiment with a tool that I've never used before called Peerceptive. So I'm still in the process of setting it up. So, but that may require, so in the past, there was a separate grade for your report and a separate grade for your peer review. So you'd upload your report or your presentation, and then everyone would peer review it. And then all the people that would peer review, I would then see who peer reviewed, and then I'd give them a check like, oh, you peer reviewed, you get a score for that. Same thing with the presentation. And then I would score the reports and the presentations as well. So you get the feedback from your students, and then you get my scores. Peerceptive combines all of that into one score that is weighted so that a certain fraction of it is peer review and a certain fraction of it is the actual score. So it's an aggregated score from your peers as well as score inputs from me. So it may change the way things are structured in the grade book, but I'm going to do my best to respect the percentages that are currently in the syllabus. And so I will weight things in Peerceptive according to the syllabus, but that may cause me to torpedo some of the separate assignments that are in the syllabus. So you might notice that the peer review assignments might go away, in Canvas. But that's not because peer review isn't required. It's because now I'm letting Peerceptive do all the aggregation and provide one grade that I then put into Canvas. So I know it's a little complicated and it's a little abstract at the moment, but that's the reason why you don't have access to the final, like, I mean, nobody's going to be uploading the reports right out anyway, but there will be some reorganization as I get Peerceptive integrated into the course. But you still should be able to submit your names and submit this input modeling report. Now, that data collection that I was talking about for that input modeling report, we've reserved a lab time, so there won't be a lab that week. So basically, so that the lab before that, we'll give you data as if it was your data and say, do some input modeling. So you have some practice doing input modeling. And then that week's lab then won't have a lab. The lab activity will be you getting together with your group and walking down to Starbucks or Chipotle or wherever and taking some data for you to use in your input modeling report. So that's kind of the plan. And I will and that's kind of the high level overview. As we get closer to these individual deliverables, I'll give more concrete reminders, but I'm just trying to give that kind of the map there. So to summarize here, you got those names of team members that's due, like I said, not this week, but basically next week. So form your teams, look at that Google spreadsheet, populate that spreadsheet, find individuals. Then this input modeling report, that's due roughly 2 weeks after that. And then at the end, the last week of the semester, basically so I make things due Wednesday so that there's time for your peers to do the peer review before the end of the semester. So it's a little weird to have things due on Wednesday. But that's the idea, is that so then there's between Wednesday and that Saturday before finals week, all the peer reviews can come in. And that way you don't have to worry about things during finals week, and then I can grade. Because the hardest thing for me is grading these final reports, these final project reports. So while you're off taking your stage 2 of your final exam, then I'm processing these reports and these presentations. That's why I need to kind of get them in before finals week so I can have all your grades done by the posting time there. So like I said, this peer review, as I kind of learn all of the nooks and crannies of Peerceptive, this process might change a little bit, but and these these scores might get aggregated together, but the percentages will still be in there. They'll just be implemented in Peerceptive. All right, so any questions about this structure of this final project report, the expectations moving forward? For now, the most important thing is to find 3 other people that you're willing to work with to gather some data and model using a relatively simple, what our heuristic is, the arena model will be a model that's sort of complex enough that you can use a submodel. So that basically means that it's too ugly to sort of present on one page. There's enough blocks that you can say that, well, really these blocks are a functional unit that I'll put into a submodule. And you can do that in Arena. So you sort of highlight a bunch of blocks, you right click and say create submodule, and it creates a little separate block for that you can drill into. That's one way to view it. I mean, the big thing is I used to have everybody give presentations in class, and then I'd have other IE faculty come and be like a little jury, and as opposed to just doing peer reviews. And in that class, and I didn't like that because we burned like a whole week, because at that time we had like 150 people in this class. And then so that would mean that everybody would just be here listening to presentations for like a whole week, and it was like no good for anybody. But the common feedback from the sort of jury of other IE faculty was always like, well, why did you need a simulation for that? And so that's the sort of thing you want to kind of avoid. It's like, you don't just want to be using your sim to demonstrate a principle that you already know exists. You want to say, I found a problem that's complex enough that I can't just use some back of the envelope calculation from 470 to solve. That I really, really don't know what the answer would be. It could be one of 2 things, and I need to run the sim, a bunch of times and see which one is more common. And then as long as it's got that, it's complex enough. So it's not going to need to be like, you will see in one of your labs this example telephone call center sim that's like super complex, and I really love it as an example. That is more than we're looking for. And so it's somewhere between the kind of drill, the factory, the whatever that drill parts processing model that we've been using, is the sort of an introductory model for Arena so far, and that giant telephone model. It's something sort of in between. And I've actually put a couple of sample reports from previous semesters, and you can see the sort of things like, people, there's a nice one where they modeled four peaks, and it was pretty complex. And that's probably the limit of the complexity you sort of need to shoot for this project. All right, so that's the final project. Like I said, formatting details, the presentations will be no longer than 10 minutes. Do not go over. No one ever complains about a short presentation. Likewise, you won't be docked if you go under 10 minutes. You'll get docked if you don't include something that's in the rubric. But as long as you tick all the rubric boxes and you have a complete and concise presentation, you might be able to finish in 8 minutes or whatever. So, but definitely, like, nobody, it's given that they're peer reviewed, I can't ask any of you to listen to more than 10 minutes of each presentation. So it's totally reasonable somebody would say, oh, 10 minutes is up, I'm done, so you don't want to go over 10. And then, like I say, written reports got a very specific format, and you can see the description online for that. So it is 4 pages. If you need more, like my model doesn't fit in 4 pages, you can say, well, you'll put figures of the important parts of your model in the report, and you'll say see appendix, because the appendix is unlimited. So you can add more things, but the report should stand alone in 4 pages. And then grades, like I said, for the final report and for these presentations, due in part from peer review. So it's my evaluation plus the peer review evaluations aggregated together. And then so names of team members. All right, so any questions about the final project report or final project? All right. Otherwise, same old, ICAs. The homeworks here, so this is going to take me a while to update the slides, but as you saw, I changed the homework policy to try to make it a little simpler and maybe a little more generous. Now there's none of this 20% per day late for homeworks. Now homeworks are kind of like most other assignments where there's a drop one, except for the very last homework J2. That's a special homework that cannot be dropped. But all the other homeworks, one can be dropped and will be dropped automatically. And I've taken the due dates and for basically every homework, and I've moved them to the end of their old availability windows. So now it's just then made the availability window 10 a.m. the next day. So it's now homeworks are just like labs. You just have to whatever the due date is, which now is a little bit later, then you just have to get it in before the availability window. As long as you get it in, there'll be no penalty. But if you don't get it in, then you can't submit it. There's no like 20% per day late before. And so I'm hoping that'll just be simpler to interpret and simpler to plan for, and just give more time to do the homeworks as well. And then keep thinking about your final projects. And so form the teams, come up with some ideas, and then plan your data collection strategy. Lab 8, this is when we're going to give you some sample data. And then lab 9, I think, is the lab that we then take off so that you have time to go out and collect some data for you to demonstrate on your modeling report that you can gather data from the system and perform input modeling. Okay. Everybody good? All right. So before, the very last thing at the midterm, we're talking about variate generation. So this was the general picture that we kind of left off from. You've got this distribution you're shooting for. You figure out what its CDF is. You invert the CDF, and then you pipe in random numbers into one side, and you get the distribution that you want out. So, a simple example of that is if you have this probability density function you'd like to draw samples from, described over here, then if you integrate underneath this curve, you can kind of do this geometrically or with the calculus. And you know that for this portion, the area underneath the curve, well, this is just a triangle. Well, that's 1/2 base times height. So there's 1/2 base times height right there. So up to this point, it's just the area of a triangle. We know that in this region, if I invert it, so this region's from 0 to 1 in the X, so that's 0 to 0.5 in the R, then I can get the inverse here, which is this square root of 2R. I chose my signs correctly. as we did here in the midterm. Then if as you keep integrating, you get into you've got the whole triangle now, that's the 1/2. And then now you're just integrating a rectangle whose base is this x minus 1, its height is 1. So that gives you this area of the rectangle here. And then so that they're right there. There's the whole triangle. Here's the area of the rectangle from 1 to x. And then that's the formula for that. So we can do the same thing. So there's the inverse for this portion. This portion's from 1 to 1.5. So in R, it's from 0.5 to 1. So we've got our inverse transform generator like that. You can pipe it into an Excel or whatever program you want. You can, so in Excel, you can do a little conditional here. We can say if I draw a bunch of random numbers in one column, then I can say if that random number in one column is in this region of R, then I use that formula. If it's in that region of R, then I use that formula. Fill down, do so you can fill, so you fill down basically, create 1,000 rows of that. And then from there, then you have to do a histogram. And so now Excel does a pretty good job, at least giving you to generate your first histogram, but at least I'm never that happy with the bins that Excel picks. They're often a little too chunky for me. So the heuristic that the book talks about, and I think most people use, is like for n samples, you often choose square root of n number of bins. So 100 samples, 10 bins is good to start with. In this particular case, where we're talking about this range from 0 to 1.5 for this 1,000 numbers, then maybe a 0.1 wide bin. That's another way you could do it widthwise. And so you create your bins. And then so the old way to do it in Excel is use a frequency function. But again, now Excel's got these graphical approaches where you just give it a histogram, right click on it, say data series, and then you can update the bins. And then you get a histogram that looks like this. And that, fortunately enough, looks, if we go back, to what we were expecting. So that's the idea here. There's our trapezoidal distribution here that we drew. If I wanted to do that all in MATLAB, this is what it would look like. So I draw a vector of 1,000 random numbers. I instantiate a blank vector basically of my x's, and then I populate a fraction of those with one formula and a fraction of those with the other formula. And then there are programs, so now MATLAB's got not only hist, but histogram is another nice facility in there. Set up my axes and I get the same sort of thing. So a bunch of different ways that you can generate that. You can also do it in Arena. So you can build a little pipeline here. So where you assign, in this assign block, you draw a random number. And then here in this formula, I'm implementing the same conditional here that I've got there. And then in lab 7, you learn that you can do real-time histograms right on the front of your model. So as your model's running, it's keeping track of data and then showing you a histogram as it goes, and it again gives you this histogram. So it all works, as expected. And of course, you could do the same thing with the other half. So for those that would like a review of that, then I've put it here in the slides. I throw this up here because one of the nice things here is you have to use a negative square root because of how this is set up. So that's an example where in order to get the right X range, you have to use a negative square root. So again, just review of that. Again, I get the histogram I want. So that's, how so that's great. Now, but the thing is, how do we choose, this, that's the kind of input modeling. It's like, if we know we want this, we know how to get these out. But I'm really interested in the other way around, where if you go out to the Starbucks or whatever, and you take your data and it looks like this, then how do we know that this is the right model that we need to be having Arena drawing from? How do we pick this? That's really the function here. And so we know, and then how do we validate? So once we've chosen this distribution and we say, okay, to my eye, that looks like this. How do we rigorously validate that it's this distribution and not something that's slightly different? Because I mean, there's variation here. Like it might be that this isn't This shouldn't be. If you just got these data, how do you know that it's supposed to be this linear ramp down and not something that's a little more curvy, for example? And so how do we build confidence? How do we validate that this here is the best fitting distribution for our real world data? And so we are going to start developing or elaborating tools we have for that. So, for example, we know in this special case that if we get data like these, we know how to compare these data and that distribution. So, if we'd say we'd like to test whether these data are uniformly distributed, we have a test for that, right? We have two tests for that. We can use the KS test or the chi-squared test to be able to compare these data to this. And if we reject this, then we can say, well, actually, we probably need to find a better fitting distribution for these data. We can't get rid of the data, but we can choose a different distribution. So one of the things that we're going to be doing in this section is figuring out how do we take the chi-squared test and the KS test that before the midterm were all about uniformity. How do we take those and now after the midterm use them to evaluate any distribution fit? So we're going to modify those two tests for general distributions. It's one of the things we'll be doing. So that's, but then the more fundamental question then is well, how do we just pick these distributions to begin with based on data that we collect? So we've got to collect the data, come up with hypothetical distributions, test whether our choices were good. If they're bad, go back to the drawing board, choose new choices. And then finally, once we get the good choices, then implement them in Arena and do our modeling, and then look at the output. So all the stuff that I just talked about was just on the input side of it. Then we'll have more stats to do on the output side of it. So that's kind of what we've got forward. So I'll skip that here. So more, maybe more motivational example here. We've seen this example before. This is a very simple security system. Passengers arrive, they get their ID checked. And then there's some process that causes some of them to get kicked out of the system, get denied, and maybe you have to go through future screening, which we just model by some random probability, and where maybe most others get cleared. So we need to figure out how to model, for example, the time between arrivals here. So there's this timeline. We gather data. And we need to then figure out how to weight the dice in Arena so that when Arena rolls the dice, it produces inter-arrival times that are close to the data that we've collected. So if these are the data that we've collected here, this histogram, this is real world data, then we might decide that, well, this is actually best fit by an exponential distribution with this mean 19.8. So we'll be able to go into Arena and say, well, this create block, I'm going to say use a exponential distribution for the inter-arrival times, use the mean from my data, make sure I use the right units. And then with that, I can let my simulation go. And after the simulation goes, so that's the input here, and this is the security system here. Then on my outputs, I've got things like how long did these these customers or these entities, as they arrived in the system, how long did they wait to get service? And that will be the outputs, and that will have its own variation. We do not fit models to the outputs of these systems. You will take data on the outputs of the real world systems, but you will not fit them. So in your input modeling report, you should be taking time, like how long did people wait in line? That's a great thing that you should be doing. Not necessarily, well, I mean, it would be great if you do it in your input modeling report, definitely by your final project report. So if you do have the ability to gather by your input modeling report and give me summary statistics, that's an excellent thing that I hope that you would include in your input modeling report. But regardless of whether it's your input modeling side or in your final report, you do not fit distributions on the output side. So I do not want to see like, oh, we took the waiting time and we fit a Weibull distribution to it. Why? There's no waiting time inside Arena that you would put that Weibull distribution. So it's useless to know it's a Weibull distribution. I don't care. It's just like extra information. But what you do with the waiting time distribution in real life is you compare it with the waiting time distribution in Arena, and you say that, okay, so the average waiting time in real life was, let's say, 5 minutes, 5.5 minutes. Well, in Arena, the average waiting time was 6.4 plus or minus 1.2. Well, 6.4 minus 1.2, that edge of that confidence interval is what, 5.2? And if I had 5.5, well, that's inside the confidence interval. So maybe my model is a pretty good fit. But if you actually, your real world data, the average waiting time was 15, and in your model, this is nowhere near 15, this 6.4 plus or minus 1.2, then you know that there's probably something wrong with your model. It's either you had a bad input model, but if you're pretty confident in your input model, then you probably need to go back to the drawing board on what's going on inside the simulation. So we got variation on the output and variation on the input. On the input variation, we fit models to it, hopefully good models. On the output variation, we compare the output variation to the variation in the real world. We do not fit models to the output variation from the real world. That's the process here that we're going through. But in this unit, we're focusing on this side, on how do we pick those? Because if we pick the wrong things for that input, then it's this kind of GIGO property that we talk about in simulation, garbage in, garbage out. The variation on the output that we are going to compare to the variation in the real world to see if we have a good model, that variation is generated by the variation on the input that just gets kind of stretched and squeezed through our model that we built in Arena. And although this model could be wrong, the other reason why our output model could be wrong is, or our output data could be wrong, is because we had bad variation on the input. So if you assume, like, let's say you go into your Starbucks and you say that, we didn't get a chance to model the variation during the work week, and so we went on a Saturday morning to the MU Starbucks and we did the got inter-arrival data there on that Saturday morning. But then later in your report, you said, well, but then later for our outputs, we then went on a Tuesday at noon, and we then gathered, right after class, we went there and gathered output data from that Starbucks, and that's what we used in our model. We used input data from Saturday morning, but we used output data from Tuesday at noon. Well, if you get a model, like if your model is built based on input data from Saturday morning, we would not expect the output data to work out very well for Tuesday at noon, because Tuesday at noon's probably got a completely different inter-arrival distribution. So that's one of these things that if you didn't show these output, if you didn't compare, you didn't do this validation step, which is one of the next units we're going to be talking about once we get through some stats, then you might say, well, based on our Saturday inter-arrival data, our proposed change to Starbucks is going to really improve operations. But it might be that your proposed change to Starbucks only works well if you've got the very light inter-arrival times of Saturday morning. When you put the very heavy inter-arrival times of Tuesday, then if you push that through your proposed changes, then maybe your changes are just as good as what they currently have in there, or worse. So that's what I mean by garbage in and garbage out, is that there are two ways you can break your simulation models. You either can have bad models here that don't match reality, or the process here matches reality perfectly, but the data you chose is just totally bogus and unrealistic. So that's why we really need to make sure we get this right. Okay, so input modeling, like we know, selects these probabilistic models. For the type of system you choose, there are certain inputs that we expect to see. So if you choose a queuing model, so if we choose Starbucks, then I expect that you're going to have at least an inter-arrival time distribution you're going to have to fit as inputs, and a service time distribution you're going to have to fit. Now, you might choose a supply chain model instead, kind of like the refrigerator thing, where you could say, well, this is an inventory management problem where you've got trying to figure out how many things to order and how much space to keep in my warehouse, and so on and so forth. For that type of stochastic model, then I'm going to expect you to have a demand distribution, which is how many orders from customers you get every day, and a lead time distribution. How long does it take for your orders for resupply to get back into the warehouse? At a minimum, I would expect those two things. For reliability problems, so if I'm modeling like how often does ASU have to send people out to fix these lights, for example, and whether they send them out when there's just one light bulb burnt out or when all the light bulbs in the classroom are burnt out, and trying to understand those sorts of problems, that's a reliability problem. And at a minimum, the input model that you should be picking there, it would be a failure time distribution. How often does a single light burn out, and how many lights do you have across the rooms? So those are the sorts of things. So as you're thinking about the types of models, you can say, does my model fit more into this, or that? I'll tell you that just for convenience sake, most project teams in this class will end up choosing, not all, but most of them will end up choosing things that fit more in the queuing network side, just because for whatever reason, it's easier to imagine those systems and gather those data. So these are probably the types of data, but occasionally you get students that, they either through an internship or through a family member or whatever, and they might have access to things that give them data that they can use for supply chain or reliability. So those are things to think about here too. But yeah, regardless, you have to choose the right inputs and then also choose whether the right variables and then whether those variables have actually the right probability distributions. And that's really important because if they don't, that can totally screw up your model, regardless of how great your diagram is. All right. So any questions about what I'm saying here? About choosing variables, choosing the right input variables? Okay, so in this unit, so we've broken it up into three parts here. So we just talked a little bit about data collection today, and then we're going to get more into the technical parameters as we go into Tuesday and Thursday of next week. So like I said, the first thing that we're going to focus on today here is the data collection part, which is again for the input modeling report. I don't need you to collect all of your data, but I do want you to show that you have the ability to collect data. So I want you to collect at least some of it, at least some pilot preliminary data. So that's why this will be kind of valid to that as you start thinking toward that. So a kind of a working example here of the complications in data collection. So uh, in this particular case, a simulation study will investigate how to reduce patient waiting time, or how to reduce time, how much time patients spend in a clinic in general, not just waiting time, I suppose. The entities there are patients. Activities might include, for example, nurse obtaining patient history. So that's the service time. So this is a queuing model, basically. Patients arrive, they queue up and wait for service, they get service, they leave. So I need to know the inter-arrival time of the patients, but I'm now focusing on the service time distribution of the nurses that are obtaining the patient history. So in this particular example, someone says, well, you don't have to go out and collect the data because we actually already did a study like this in 2002, and we have data on how long it takes nurses to collect data from incoming patients. So those data are available. You don't have to go out and take those. So should that be used? What are the potential problems with using these data from 2002? What do you mean by outdated? Yeah, right. Absolutely. Technological advances. That's so if you, I mean, I don't know how often you guys have, like just over my lifetime, I think going to the doctor's office has changed 4 or 5 different times, like the experience. So gone from paper-based forms to, to computers mounted on walls to tablets. And then even once they're in the computer, the software structure, goes from they have to do a lot of manual typing to, to checkbox and whatever to now AI sort of helping them sort of, fill that out. So a doctor's office is a very dynamic place. And so it might be that service time distribution, like it might have taken a very different amount of time. It might have been longer, it might have been shorter. It might be that it actually was shorter, clearing the nurse in 2002 than it is today. But the extra investment in time with the nurse today actually makes it quicker with the doctor later. I don't know, it's hard to even predict which way or whatever, but the idea here is that basically a nurse of 2002 is not a nurse of today. So that's an example that if you have a data set, and let's go through your input modeling things too. A lot of times we'll have students to say like, oh, my family's got a guitar shop or a guitar manufacturing line or whatever, and they actually did collect data on how long it takes to manufacture these guitars or maybe inventory things or whatever. And then you have to say like, but this data was from 1995. And then you say, well, has the things changed since then? So you honestly don't just use data because it's available. You have to really evaluate, is it still valid? So another example here. So simulation study will impact a new security protocols for, so this is our metal detector feeding a government building example we keep coming back to over and over. So entities here are people, so it's another queuing system. So inter-arrival times and service times. So again, we're focusing on service times. So the time to pass through the metal detector. 1,000 observations of people passing through the metal detector are recorded. The mean and standard deviation are nearly identical. So somebody just looks at the summary statistics and they say, the mean and standard deviation are identical. What's a good distribution to pick? Well, if you think back through the continuous time distributions that we have, then we know that an exponential, for example, is one of these rare distributions that has a single parameter, and that single parameter represents both the mean and the standard deviation of the distribution. So you might look at that and say, well, if the mean and standard deviation are the same, then most likely an exponential is probably the good one to pick. So then, though, if you actually look at the actual mean, then you say, well, but the mean passage time through the metal detector. So this is the time it takes to walk so the metal detector's here, and I walk through the metal detector. That's what they're talking. They're not about the time in line. They're just talking about like once you reach the metal detector and they say, okay, go, then this is the time it takes to walk through. And you notice that the mean passage time is 30 seconds. So in this case, this is like why it's valuable to have domain experts. And in this particular case, everybody who's been through a couple of different security screening processes is a domain expert. And you can sort of say 30 seconds, that means that on average 30 seconds. So sometimes it's less than 30 seconds. A lot of times it's more than 30 seconds. Does that match your experience? To me, that seems like a really long time to walk through a metal detector. So that kind of suggests to me that I need to look at the data more closely. Simply knowing that the mean and standard deviation are identical, simply looking at the summary statistics is not always a good idea. So when you're doing these complicated models, you got to look at the distribution. Once you look at the distribution, then that might release you to look at the summary statistics and make decisions based on the summary statistics. But just looking at the summary statistics is really dangerous. Because if you look at the histogram of these data, you might find that it's bimodal. So there is a small peak of that maybe goes from 0 to 6 seconds, and then there's a lull, and then suddenly there is a large peak that goes from like I don't know 45 seconds to a minute and a half. And so the interpretation of this bimodal distribution is actually mixing the term we use two other distributions, one distribution for individuals that pass through and the metal detector doesn't go off, and another distribution for individuals where the metal detector is triggered, they have to get a pat down and then they have to go back through. Because if you find out that actually the way the data were taken is that they actually do, it's when you first went through the metal detector and then when you left the metal detector area, if those are the two endpoints that's where they're generating the service time distribution for, that can include this other process of rescreening. And that might be where this extra high peak is when the metal detector is triggered here. So it's definitely not exponential. And that suggests that I can't just use a simple create process, collect, sort of setup where I'm probably going to need structure where I've got some individuals pass directly through the system and other individuals go through a totally separate process. So sometimes looking at the distribution of your data, if you can't fit one of those many continuous distributions that we've learned about, we've added to our vocabulary, the solution is not necessarily to find another distribution you haven't learned about before. The solution is to say, if I add a few more blocks to my model, does it break these data up so that this crazy distribution turns in to a mixture of distributions that I do know what to do with? And that's an example here. And we'll actually work through an example here, I think, the beginning of next time. So another example of that, let's say we look at those passage times, some of them might be negative. So that means that that might just be a mistake in the calculation. Maybe these are fixable. So maybe for some reason, like somebody was manually deciding which one to subtract, and occasionally they kind of flipped the order. And so those negative ones are real data. You just need to flip the sign on those. But you don't just want to pipe those in and fit a model to them, because you should never get negative passage times. It might be they're truly garbage data, and if you discard them, but the worry is that if you discard them, is there a correlation between some important event in the system and these garbage data? So maybe the reason they're garbage data is something happened that upset the modeling process, and if I just discard them, I'm going to miss out on whatever that something was. So you have to be very careful about discarding them, but you can't leave the negative ones in, because the negative ones should not affect your passage times numbers. So looking for, knowing, you got to know in your head, for this type of variable, what do I know about its range? And a lot of times it's just, is it positive or negative? And there's a lot of things that just can't be negative. And so you scan through and make sure, do I have any negative numbers as a sanity check? And then but then you have to decide, well, okay, if I'm estimating another variable, like the probability of triggering the metal detector, maybe the passage time information, I can't use that to fit the passage time distribution, but maybe these data still might be useful in, maybe I can still infer from those data if this was an individual that got triggered the metal detector or not. Like, you might find that it's trash data, but you might find that all of the trash data come from individuals who triggered the metal detector. There are other people that triggered the metal detector as well. So in that case, maybe discarding them it might be what I want to do for the passage time information, but maybe not for the probability of did they trigger the metal detector. So you really have to get very close to your data and make a lot of decisions about these weird numbers that you get, because they're going to happen. Yeah, so how do you sort of anticipate these things and try to prevent these errors from happening? So one of the things is pre-observation and planning. So with your final project team groups, as you form them, I want you to sort of be thinking about ahead of time, what do you think the input models will be? That's the first thing. But then drill down a little further. How are we going to measure that? What are going to be the complications of measuring that service time? Well, for one, if there's a really long delay, for example, a really long wait, I can't measure the service time for when they enter the queue, because that's delay, that's not activity. I'm gonna have to follow that person until they finally hit the front of the line and then put in their order. That's when the service begins. So that's, one of the things. So try to anticipate these issues ahead of time, and and maybe actually go into your system and don't take data. Just go there and say, imagine we were taking data now, what would be the problems that we might get? And then you have to be careful about this, but when you do start collecting data, when I say analyze it, you don't want to prime your data. You don't want to sort of say, like, wait until you get the result you want and then stop. But you do want to at least upfront do a sanity check and say, am I getting negative numbers out here when I should be? So, don't wait to look at your data until after all of your collection is done. If you're planning on, going to that Starbucks and for an hour a day for a week, taking data, and then you'll have all your data done, after your first day, go and just look at that data, like right then, and just make sure, did I waste my time that hour? Because it's a lot worse to waste a week than to waste a day. So look at your data ahead of time there. So, and is it adequate? Can I actually generate the distributions and the parameters I need to go into Arena with these data? Do I need more finer scale data? So again, a big problem we have in the final project report is a lot of times students will come to me a week before the project is due, and they'll make an office hours appointment, and they'll show me your data, and they'll say, we don't know how to get the service time distribution out or something. And it will be because that problem I just mentioned, where they marked when people entered their system and entered the line. They marked when people exited the system, but they didn't mark when they went from the line into service. And so based on the queue length, they get different service time distributions. And you can't incorporate the waiting time of the queue into your service time distribution. So just finding that, it's good to know how long they waited. That helps with validation later. But for input modeling, you got to know when they go into service. So, those sorts of things, like, did I actually collect enough data to pull out the service times and not the total time? That's not trivial to do. And that's something that is often missed in the projects that we do in this class. And then this is check for homogeneity and combine. So this, a lot of times, in order to get enough data to make a convincing fit, you might need to gather a lot of data. And if you think that your Monday and Tuesday distributions are going to be very different, like if you think Monday at noon is going to be busy, but Tuesday at noon won't be, then you might need several Mondays in order to get enough data to fit the Monday distribution, and several Tuesdays to get enough data to fit the Tuesday distribution. But it might be that when you actually look at the data, just your pilot data, that the Monday numbers are very close to the Tuesday numbers. And you realize that there's actually just a single weekday here, that every weekday at noon has basically the same distribution of inter-arrivals. At that point, you can pool your Monday and Tuesday data together into one data set and then fit a weekday noon just based on those. So that actually reduces how much data you have to collect. So look for what we call homogeneity. So that's look for similarity in distributions. But if you need to, or you could say we're only going to model Monday, and then that way you only model Mondays or something like that, and then you don't have to worry about that. But if you are trying to model a week's worth of activity, then it might be that there's a bunch of things you can pool. There are things you can't pool. So there's going to be inhomogeneity across hours. So Monday at 10 a.m. is certainly different than Monday at noon, is certainly different than Monday at 3 p.m. Those probably need to be split out. And when you talk about scheduling in the Arena lab, that we'll do, then it talks about how you can put in different inter-arrival times or service times on a schedule. So when it comes to this example, you pool across days, but not within days. Now, there might be a couple hours you can pool. It might be that 9 a.m. and 10 a.m. are the same distribution. Pool those together, fine. So you might have just a morning, an afternoon, and an evening distribution. That's totally fine. But you have to make sure you only pool across things that where the data appear to be similar. And we can talk about the stats that you need to sort of justify whether they're similar. So that's kind of what I'm sort of suggesting here. And then be aware of possible censoring. So what do I mean by that? So if you were to say, I want to model the failure time distributions of these light bulbs, what is a problem with that? Does anyone have a guess of, like, you have no idea what the failure time distribution of this fluorescent light bulb is. So you're going to gather data on it. Why is that impractical for a semester project? Yes, much longer than a semester. Absolutely. And that is going to result in censoring. So what we mean by that is if it takes 6 years for this fluorescent bulb to fail, over the semester, you're going to estimate that they never fail because you won't ever observe a failure. And so in your distribution, you're going to say no failures. And that's just because you didn't watch for long enough to actually see the failure. And so that is an example of data censoring, that if you censor, in a sort of confounding way, then you can end up getting a predicted failure time that is much longer than normal just because you didn't witness it. So that's what we're kind of saying in here. So censoring can bias your models towards to different failures. So it can go the other way as well, quick failure times. So let's say you did happen to witness a bunch of failures in one semester. Well, because you witness all those failures, then because you didn't wait for the long failures, then you can get a bias in the other direction. So if if the outcomes that would if a representative sample of outcomes includes outcomes that are impossible for you to measure, it can bias the distribution. So if you only can measure short failure times, then you get this, where you can bias your data towards quick failure times. If quick failure times never happen in your distribution, but you can't ever witness the ones that can happen, then that's another example where you can actually shift it the other way. So you have to be cognizant of, like, if you go to the Chipotle or the Starbucks or whatever, there probably are pathological cases throughout the day where someone waits for over a half hour for their coffee. MU Starbucks, I'm sure it happens. But if you just happen to be at a time of day when that never happens, then you might not be there to witness whatever weird stuff is happening with their service that generates those cases. And that can cause you to sort of bias that data set. So be careful about data censoring. The other thing is looking for relationships between variables. And so here's an example where I've plotted inter-arrival time data and service time data. Now, most of the time, you might expect that these would be independent. So I've got a distribution here on this axis of inter-arrival time, and this is my distribution of service times. So this is saying for each dot here is a customer that arrives, and they arrived with a certain inter-arrival time after the previous customer, and they received service with a certain service time. So if I plot their inter-arrival duration and their service duration, normally they would be independent. Well, we might expect they would usually be that these two processes do not relate to each other. So these two distributions don't have any pattern. But it's good to verify that, because there might be some weird thing that when you arrive very close to those in front of you, it somehow sets up a correlation where there's some sort of memory in the system where maybe the person providing service now feels overburdened by the number of individuals that all showed up at the same time, and then that changes that service time distribution. And so I'm not saying for this example this pattern makes sense for that, but it might be that your inter-arrival times here, when they're very low, so are the service times. And when the inter-arrival times are very high, so are the service times. So notice the cigar shape here. So when you plot these two things together, look for correlations to see, because if there are, then you might be that you only need one, for example, inter-arrival time. Like, you may not need to gather inter-arrival time and service time data, because service time data might itself be a function of whatever the inter-arrival time was. So it might be that when you actually fit a line through this, that you find that, well, if I just multiply the inter-arrival time by 2.5, and then I add a little residual noise to it, then I pretty much get my service time distribution out, and I get this cigar shape. So that's an example here of building a statistical relationship between that. And how would you implement that? Well, you can go into Arena and you can implement this relationship. So you can draw a service time after you basically have Arena draw an inter-arrival time according to some distribution, and then you can have Arena do this math. So it'll draw an inter-arrival time, it'll draw a normal, according from this distribution, it'll add the two of them together. And then you can, for validation, compare your new simulated service time distribution with the real service time distribution and compare the relationships between the two. And there you go. So if you missed that relationship, this would be a really important relationship, like to know that when you get bunched up arrivals, the service times happen to be faster. Like in this case, it might be that the people working at the restaurant see, wow, we've got a huge line, let's work faster. So bunched up inter-arrivals might mean quicker service, whereas inter-arrivals that are spread out might mean a little lazier service. And that would certainly affect the operations or the dynamics of the system. So it's really important to gather that. And the other relationships you have to worry about are relationships over time. So autocorrelation. So this is an example of if I've got samples here. So these are maybe my interrival times. So let's say I've took you're not probably going to take a data over 1,000, but let's say I took 1,000 customers, and these are their interrival times, or in this case they go negative. So it's some other data. These are just data I generated, sort of synthetic data. But so this is customer one, this is customer two, and so on. So 1,000 customers here. And these are independent. So if you know one customer's value, you can't predict a customer right after it. This is what independent would look like. If you were to plot a customer against the customer that happens 10 customers later. So you know that this is customer, whatever, 20 or 120. And so we go to customer 130, we grab that, and we take that pairing and we just sweep that over the whole thing, and we plot those pairings across here. Then this has no relationship. So for at least a delay of 10, there is no correlation. There's no so-called autocorrelation, self-correlation between here. And this case here, this is what we refer to as white noise. So the term white noise means that any data collected doesn't predict anything about data later. That's white noise. But an opposite case would be this. If you look at your data, and because we haven't gone into a lot of the sophisticated tools you can use to parameterize these things, if your data look roughly like this to the eye, I'm okay with you saying, yeah, those are independent. But if you look at your data, it looks like this. So then you can see that there is major autocorrelation. So if you know you're up here, you're going to stay up here. If you know you're down here, then for at least a few samples, you're going to stay down here. So if you see this sort of patterning across your samples, then that suggests that, well, if sample number correlates with time, then maybe you actually need to view these as like windows where you could say, well, I'm going to model, like I'm going to need to, this goes back to the homogeneity thing. This is sort of an inhomogeneous arrival process where you could say, well, maybe instead of treating all of Monday as one day, I need to do morning, afternoon, and so on, because within these small groups, you might have a little bit of independence because this group as a whole stays up here, but maybe there's still some randomness within here. You know that this group is not going to jump down to here, but if you just restrict your view to just these here, there is a little bit of independence. So if you chunk it up, then maybe you get some of your independence back. Maybe that's one way to deal with that. Or maybe you just need to simulate this pattern. And that's what I'm going to show here in a second. And so if I were in this case to do that, take 1, add 10, and then plot that pairing together, I would get this cigar shape here, which shows that the current value predicts the value 10 samples later. And if I were to use a correlelogram, which we'll see in the output analyzer as an option for you to do, this sort of does this across all of the different lags. So not just 10, it does it for 1, 2, 3, all the way up through 1,000. And this is showing the predictability. So if you're right on top of the 100% predictability from one point to itself, and then if we go down to this lag, which is, I don't know, at 25 or something like that, then you lose predictability. But you go a little bit further at 50. If you know a point, you know that the point 50 times later has at least a pretty significant probability that it will be the opposite sign of this point. That's what this is showing you. So in white noise, this correlelogram would have a peak at 1 and would be 0 everywhere else. But when it's not white, when it has color, then you get something like this. So just look for patterns like this as you plot all your data together. If it's a time-based pattern, you can use schedules like I was just saying. So you can slot those up into times. So you could say this is morning, this is afternoon, whatever. You can also create these expressions where if where you can sort of, there's a t now variable in Arena where if you could model this, like you'd imagine fitting a cosine to this, and you can say that actually these data are drawn from this distribution where I've got this clock that is rotating around at this frequency, and then I add a little bit of noise to it. So that's something that you can do to mimic these sorts of patterns. But most of the time, when you see this in your data for this class, a schedule is the right way to go if we're talking about things like inter-arrival times or service times. And then there's other patterns that we can do here. So, but the big thing is the scheduling. I'm just sort of driving home, use your schedules. And then another, I'm almost done here, but I've already emphasized this, but understand the difference between input and output. So when you're doing your input model, there will be teams, there's always teams every semester that show me a histogram of output data, waiting times, queue lengths, or whatever, and then fit it to something. And there's no reason to do that. So output data they vary with operational decisions. They aren't things that you put into your model. They come out of your model. So you don't fit input models to them. So you really have to understand like the difference between inter-arrival times and queue waiting times. You need to gather data on queue waiting times, but not because you're going to force Arena to have those waiting times, but because you're going to need to evaluate Arena's outputs to see if the waiting times that Arena generates are consistent with the waiting times you see in real life. So the output data is used for validation of your simulation model, as opposed to the input data where you can't even run the sim without the input data. So knowing the difference between these is really, really important. And do not fit input models to output data. So most people won't do that, but there will be a few teams that are going to do that, and we'll mark it. Say like, why did you do this? Like, what do you think you're going to use this input model for on this output data? Like, who cares that the waiting times look Weibull? What do you do with that information? There's nothing to do with that information, so don't do it. And that's sort of, those are like my key sort of tips for data collection. So on Tuesday, then we're going to say, well, now that we've got the data, how do we identify the probability distribution and evaluate our choice? And then on Thursday, once we feel good about our distribution, how do we pick the right parameters of that distribution and evaluate our choice? And that's kind of what's going up. So any questions on any of that from today? All right. So I'll just do the one eye clicker for today. All right. And so the what I have the question I have here is, should you fit a probability distribution to queue waiting times? That's my question. Yes or no? Is it a good idea to fit a probabilistic model to queue waiting times? That's all I've got. Have a good day. Yeah, I mean, I was just sending an email, but like, I don't think he sent the last one, like, something after 4 weeks. So, no, I don't know. I didn't show up, but yeah.